Welcome to PlanetGeo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Get right up in there. Get that beard just right up and nice and tight into that microphone, Christopher.
It is. I don't have any food on it today, so I won't be smelling what I ate.
Just what a delicious vision for the listener listening to this, thinking about Chris Blyce's beard and leftover tidbits that he keeps in there. I mean, my goodness.
Well, what you're referring to was way more than tidbits. It was more like a smearing.
That's true. I did call you the other night, and what was happening? You and Jenny, I think I called you, and you were sitting on the couch with Jenny doing something, and right away you launched into like how good your dinner was that you had. And so I had to make a snide remark about how much you had of it left in your beard, and all I could hear was Jenny dying laughing in the background. I don't know if I was on speakerphone or not, but all of a sudden I heard her
you were for sure
dying laughing. That made me happy.
I can't remember what we ate, but you know this about me. I am a foodie. I love to cook. I love food.
Hey, Chili Cook-Off award-winning Bullheis family recipes. I mean, yes, definitely.
I know. It could be an episode.
Oh, man. So, Chris, you mentioned before that your mom was composing an email to us when you went and visited on Friday. I don't think I saw it hit our inbox. What happened?
I don't know. This is so funny. So my mom and dad, they're loyal, okay, as they should be, but they are so funny. So I walk in on Friday after work. I try to go over there every Friday afternoon, be a good son, and talk to them for an hour or two. So anyway, my mom is right in the middle of composing an email to us, but apparently she never sent it because we never got anything. But they're very confused. She said, "I'm halfway through your episode on granite countertops," but she said CampGeo, and I'm like, "Mom, no, I think that's PlanetGeo. That's not CampGeo." She's nope. It's CampGeo. And I'm like, "Well, show me, Mom." So she's not on her phone at all. She's on her computer, right? And so she goes to our website. You know how we have everything kind of organized by topics?
So the PlanetGeo website or the
PlanetGeo website, but we have CampGeo linked in there. The bottom line is my mom and dad are thoroughly confused on the difference between.
Okay. It is a fair, it's a slightly fair, let me say, I understand the confusion. We didn't do the best job. Like we initially started out with CampGeo being like our audio visual textbook, like the introduction to the geoscience thing. Then we just adopted that name for the app. So it's the CampGeo app, which has more than just CampGeo content in it. And so I can see maybe where they're getting confused, but especially if you listen to the podcast on our Planet Geocast website, then that would be very confusing because it's just in your web browser. They're all accessible.
She's very confused.
Oh, that is so funny.
Anyway, so then my dad enters the room and he's like, what's going on? You know how my dad talks like that. Yeah. and I explained the situation and I said, trying to explain the difference between CampGeo and PlanetGeo, and I was unsuccessful, by the way. It's just muddy waters.
Mass confusion.
Anyway, I'm like, "Dad, have you listened to our guidebook to Yellowstone National Park yet?" And he's like, "Well, no, I don't know how to get it."
Oh, no.
So, yeah, it's mass confusion over there.
Mass chaos
right now.
over at the Boys senior household. Oh, man, that's very funny. Well, I hope nobody else is having that issue. And if you are, let us know. Send us an email, planetgeocast@gmail.com. And
Jesse,
we can
should
help.
we just real quick explain the difference? PlanetGeo is our podcast, right? It's our just a straight up podcast. That's what we're doing right now.
It's kind of where are you accessing this? If you're getting this on your Apple Podcast app or your Google Podcast app or I don't know,
Spotify,
Pocket Cast, whatever, you're listening to the podcast PlanetGeo. If you're on our mobile app, the CampGeo mobile app, then we have some podcast episodes uploaded there, but not this one. So this is
right.
Not that.
But it's also the CampGeo is where we combine the audio and the visual together with this kind of like new thing that we've developed. So.
And it's a little confusing, Chris, because we made a web app first instead of a mobile app. And so we're start spinning down the web app and just transition to the mobile app only, basically. But I could see where it's confusing because it's been a while. This has been a work in progress for a long time. But you got to help them out. We need some IT support over at the Boys household.
I try. Oh my gosh. I try.
Oh my goodness.
I do my best. Yeah.
That's very funny. Well, okay. Today, Chris, this is certainly not CampGeo. This is not introductory. Well, it's kind of related maybe to introductory content, but we're not going to we're going maybe a little bit in the weeds here. Potentially. We might stray into the weeds for a little while.
Absolutely. And Jesse, that's interesting because you and I have this kind of conflict with this of how deep do we go into this? Because our goal right from the outset of doing this podcast was to make geology and the study of this amazing planet that we have relevant to everybody, relevant to the masses, so that many people can understand it rather than the few. And that's always been our thing. But we've gotten some recent emails where people are asking, hey guys, don't be afraid to go into the weeds. Like
totally.
I want some of the weeds. And
so here's we're gonna get a taste of the weeds today, probably, but also we're gonna bring it back home. And Chris, what we're doing here is we're talking about Bowen's reaction series, and maybe it's Bowen's reaction series revisited because we've done this before. Well, we covered the basics of Bowen's reaction series maybe a year and a half ago or something. We also have an entire episode on the CampGeo course content on Bowen's reaction series with some really nice images. It's in the Igneous Rocks chapter. So you can go to the Igneous Rocks chapter in CampGeo and get access to all that for free right now. So if you want the images to go along with this, that's a great place to do it. We're going to do that plus some, I think, in this episode, plus some conversation about what Bowen's reaction series is. So Chris, why this episode? You kind of, initiated this, I think, and what's the motivation for you?
I think because being as old as I am, I was brought up more in a kind of this classic way, my geology training and Bowen's reactions.
Pre-plate tectonics.
Actually, it was not, but close.
Okay.
But anyway, Bowen's was kind of presented as this very broad, really important concept, and it explains a lot, and it just kind of makes everything fit together. It was just kind of this unifying thing, if that makes sense. But the older I get, the more I come to realize that it's very highly idealized, and the older I get, the more confused I get in terms of where does this actually fit within the context of what do I want my students to learn, or why is this important for people to know that are not geology majors? Why should they know about what's going on with the way that igneous bodies or magma chambers cool off, or the way lava cools off, or the way rock melts? Why is this important? Because I know it is. It is important to know about and think about, but I guess the older I get, I get confused a little bit more.
So we have a confused Chris Ballheis with us today. No, I think it's totally fair. And I, frankly, I struggle with this too when I'm teaching the physical geology course. I would love to teach an entire course on igneous petrology.
Why don't you?
Well, we don't actually have one at Penn State. We have a blended one that my colleague teaches that's a sort of blended between igneous and metamorphic together. Our curriculum is not, it's more open to the students' choices, so we don't have a required igneous petrology class.
Okay, but that's actually my point. I'm really interested in this, actually. Why don't you start a course, and if they like it, they'll sign up for it? Can't you do that?
You can, but, it ends up being... if it's not a required part of the course and it's not tied in with you'd want to have a metamorphic rocks course as well and a sedimentary rocks course, and we'd have to have a mineralogy course. So we'd kind of have to revamp the curriculum to make it really flow. Right now we have the basics are covered in the 200 level courses. So we have basically it's called earth materials, but it's basically rocks and minerals in one course as a lead-in. And then the 300 and 400 level classes, students can kind of pick and choose whatever they want to take and whatever's offered at a given time. So there's this kind of trickle-down effect. If I made an igneous petrology class, we'd have to bookend it with all the other stuff, and we'd probably want to require it.
Is that true? You would have to do that? That doesn't make sense to me.
You wouldn't have to, but you don't want to offer too many different courses that are similar or that have some part of the Venn diagram that's overlapping. And so we're actively thinking how to revamp this at the moment, because there are some better ways to potentially do this. When I went to Alberta, in University of Alberta, which is a Canadian system, is very mining focused. The geology majors graduate there with a really unbelievable knowledge of rocks and identifying rocks. So they had a Mineralogy 1 class, they had a Mineralogy 2 class, then they had igneous petrology, metamorphic petrology. Only the fourth year were students able to kind of select what they want, and most of them took an ore deposits geology class. So they kind of had this really coherent, consistent flow because they have to get certified to become professional geologists to work in the mining sector. The U.S. system, we don't really have as much of that, as big of an industry tilt. So, the structure has just sort of changed a little bit more. Anyway, did you have an igneous petrology class at Grand Valley?
Yes. Well, I'm trying to think. It wasn't called igneous petrology. It was just called petrology.
Okay. Did it? Because that's what I had.
Lots of thin sections and microscopes and things like that, right?
Because that's what I had, and we covered everything: sediments, metamorphic rocks, and igneous rocks. And this was at Hope, and this was... So I didn't get a lot of igneous petrology in there. Anyway, back to the point. The point is I struggle with how deep to go when I'm teaching this intro class. Like, I want to talk about this a lot, and I do end up talking about it more than I probably should. But I struggle with where to cut this off. Like, do I just talk about Bowens for a lecture, or do I talk about some different aspects to it?
So, Jesse, let's get into Bowen's reaction series a little bit. Let's do like a brief review of what it is. And then, I want to know why you think it's important for people to know about Bowen's reaction series. And I can maybe share why I think it's important. We can go from there, and then we'll go into the weeds later on then. How's that sound?
Yeah, absolutely. Let's do it.
Okay. So, all right, you want me to kick it off? What do we got going?
Yeah, well, I'm curious because, it's been 20 years since I sat in your class and learned this from you. So let's have it again.
Okay, well, I guess Bowen's reaction series, to me, the way that I begin introducing it is by talking about how minerals crystallize from a cooling body of magma or lava flow, but magma, because we want this thing to cool off slowly. It's this idealized setting. So it gives us this order in which the silicate minerals crystallize. And the silicate minerals are the most important mineral group that exists on the surface of the earth. Minerals that have silicon and oxygen in them, and that's how I start with it. But then the opposite of this is, I think, just as important is, well, if it explains the order in which minerals crystallize, then it also explains the order in which minerals melt. And so that's how I start with this. And then lastly, I'll talk about, all right, well, here's Bowen's reaction series. You guys know what it is. And we'll talk exactly about kind of like, I explain it as a big why.
Yeah, that's a good one.
But then if they know that, then let's look at this again and talk about mineral stability then, in terms of what minerals are the most stable at the surface of the earth and what minerals are the least stable. Because to me, those are the three big things that why it's important for my kids to know this.
Gotcha.
Students.
Okay. So let's maybe dive into the why now. I mean, I think this is the visual that we want to paint is Bowen's reaction series is a Y, standing up straight, capital letter Y, and temperature is the scale from the bottom of the Y to the top of the Y, where the top of the Y is hot, the bottom of the Y is cold. Cooler, let's say cold, quote unquote. It's still 500, 600 degrees or 700 degrees.
And when we say the Y, if everybody can just imagine gigantic Jesse Rymank singing YMCA, and the Y is when Jesse is outstretched arms all the way up to his fingertips. That's what we talk about with the Y.
Wedding reception, just singing the YMCA on the dance floor. Absolutely.
Right on.
So let's start, Chris, and we're going to be looking at the Y. Let's start on the left side. The left side is, and I think you probably call this the discontinuous series as well, right? The left side of the Y as we're looking at it?
Correct. Yep.
Yeah, okay. Basically what this Y tells us is there are minerals along the Y, both the arms of the Y and the trunk of the Y. And what this graph is showing us is when do those minerals crystallize? If you go from the top down, if you take a magma, high temperature up at the top and cool it down, or if you take a rock and melt it, start at the bottom and heat it up gradually.
Let's work our way top down. And so the tips of your fingertips represent the highest temperatures. So imagine a massive body of magma, and we're going to allow it to slowly cool off. And so we're going to work from our fingertips down our arms to the trunk where the Y meets.
Yeah, let's start with the discontinuous one, the one on the left. And this is a series of minerals that are not the same mineral. I think it makes more sense to start there because is that where you start, Chris? You talk about discontinuous.
Absolutely.
Makes more sense.
Yep.
These are different minerals. We'll get into solid solutions on the other side of the Y, more complicated. So let's start here. Discontinuous. We have minerals. We start usually with olivine at the top. That's the highest temperature crystallizing mineral.
Right up at your fingertips. Yep.
Right at the tippy top. Then we go to usually pyroxenes or clinopyroxene or orthopyroxene, depending. You have your pyroxene group of minerals there. Then you have your amphiboles, and usually it ends with biotite. That's kind of the discontinuous. And the biotite's right down near the Y, kind of by your shoulder if you're standing there doing the YMCA.
Right on. Right where the Y comes together at the base of the trunk then.
Yep, exactly. And those minerals have different compositions. They have different stability ranges. Obviously, this is temperature, so we're talking about temperature. And so they're stable at different temperatures. That's the point here.
So there's another thing that happens though, Jesse, as you go from down the discontinuous series, you go from olivine to the pyroxenes to the amphiboles to the biotite. As these early minerals, the tip of your fingertips, the olivines, as those minerals are forming, the magma that is still magma, because now you have crystals that are suspended in this kind of like mush, right? This magma mush. The olivines have crystallized out. Therefore, the magma that's left becomes richer in silica. As the newer minerals come out, like the pyroxenes, they're going to reflect that changing magma composition. And so the bottom line is that as you go from one mineral to the next mineral to the next mineral down to biotite, they are incorporating more silica into their structure.
Yeah, Chris, that's exactly right. And this is kind of where the sort of spidey sense starts to go off, that this is starting to get confusing now, right? Because, and I don't quite know if this is a point to kind of cut it off for the intro class or whether, but I go beyond this. I go like into the weeds here at this point when I'm getting to this, because we're changing two things. The way you described it is, okay, we've got olivine forming, it's fractionating out, it's going somewhere else. Usually we picture it dropping to the bottom of the magma chamber, and the magma's changing. But we're also dropping temperature. So we're kind of changing two knobs at the same time, which I think adds some confusion. So you might be thinking, well, what happens if you only change one knob at a time? Or what happens if you change three knobs at a time? Like, does that make sense kind of where we're going? And we'll come back to this, I think. But let's leave it there and talk about the continuous side of the reaction. Does that work, or do you talk about this point more? No, that's fine.
I do. I actually do. Yep, I'm drawing this up on the whiteboard as we're talking about it, or I'm on my iPad drawing this out in front of for the students. So, yeah, the continuous side. So now let's go up to the right part of the Y, your right arm, all the way up to your fingertips. What you have then is a mineral. It's a feldspar. It's a type of feldspar that's called plagioclase. But this first kind of plagioclase is really rich in calcium. So we call it calcium-rich plagioclase.
Yeah, right. Okay. Very, very cool name. Another word for it is anorthite, and so we'll call it anorthite is a calcium-rich thing. And this is what's called a solid solution. So we have the same. It's actually the same mineral, the same structure. We're just exchanging elements in there, and the exchange of elements is dependent upon temperature primarily, also pressure. But as we drop the temperature, the plagioclase is happier with more sodium in it. Imagine a crystal lattice. Imagine like a skyscraper. The steel beams are all connected there. At high temperature, it's happy with a lot of calcium in there. At lower temperature, it's happier with more sodium in there. And so we're doing this solid solution. We're changing the composition, the chemistry of the lattice, because it's happier, thermodynamically happier at different temperatures. So as we go from high calcium content at high temperature, that's anorthite. As we go down, we get to albite, which is the sodium-rich plagioclase. And plagioclase is the mineral group, and albite is the composition within there.
That's right. And we call this the continuous series because, as you just said, it is the same mineral. It's plagioclase feldspar. It's just changing its internal composition from calcium to sodium rich as it cools off, as the magma cools and crystallizes.
And then, Chris, we hit the Y, we hit our chest now, and we're moving down the trunk, down the body of the Y. And this is relatively simple. We just get kind of our lower temperature minerals, our muscovite, our potassium feldspar, and quartz are usually the ones that are listed on a Bowen's reaction series sort of plot in your introductory textbook. And these are the low temperature minerals, the ones that'll crystallize out of the last dregs of a magma chamber. Really high in silica. We've driven up silica by removing all of that other material. We also have to point out that this is, in the idealized sense, this is a reversible kind of process. So we can start with a rock, and we can start at 500 degrees centigrade, and we can heat it up. And the first minerals to melt as we move up our body at the start at our feet and move up our body to the Y, the first minerals to melt will be muscovite, K-feldspar, and quartz. That's your typical first melt to form in a rock as you're heating it up. So you kind of think of this as a reversible process.
And it's such an important thing, this reversible process, because this is how rocks that tend to be more felsic, which just means richer in the quartzes and the potassium feldspars and muscovite and so on, and maybe the low end of the Y part of Bowen's reaction series, that lower end, you generate then these felsic rocks from a different parent rock. And we call this partial melting. It's a really important thing that explains how common some of these rocks are.
Yeah. I mean, we talked about this 2 years or 3 years ago, even, Chris. Like, I think our title of our episode was something like, Why Do Continents Exist? And it's because of Bowen's reaction series. Like, this is this distillation process that we're talking about. Whether you do fractionation, start with a basalt, and the last dregs are going to be quartz, K-feldspar, and muscovite. That's a really continent, quote unquote, continent-like composition. It's this distillation process. We're kind of looking at distillation in the rock record here. Okay, where do we go from here, Chris? Is this where you cut it off in class? And is this where Confused Boheis arrives on scene, pulls up in his...
Yeah, it is, actually. So let me throw this back to you, Jesse. Here's my question. Why should people know about Bowen's reaction series? And you have the floor, okay? Like, take this whatever way you want to go. What I'm asking is, why is it important? Or maybe what that means to you is, what are the shortcomings of it? What doesn't it maybe explain? I don't know. Take it wherever you want.
That's such a
There's
good
a
question,
reason,
Chris.
Jesse, that we've had, 3 episodes on Bowen's reaction series on our podcast, right?
Yeah, it's true. Okay. Why should students learn this version of Bowen's reaction series, what we've just said? Like, why should intro students learn this? I think it's really important to provide the concept of different minerals crystallizing at different temperatures and the concept of magmatic differentiation. So if you picture a magma chamber, like what I do, Chris, in my classroom, I lecture in this big lecture hall. There's 200 students in the classroom. And I say, pretend this big lecture hall is a magma chamber and it's really hot. It's 1200 degrees centigrade. And then it starts to cool down and olivine crystallizes, and maybe we get 10% olivine crystallizing. That stuff's all going to sink to the floor of the classroom now and fill up 10% of the classroom. And then we're all going to have to stand on top of the olivine crystals. But the magma we're kind of swimming in has changed composition. It's lost olivine, so it's lost its magnesium and iron. And so it's changed composition. We changed the recipe. That process, I think it's a really fundamental concept that you can't really explain easily without going through this simplified version of Bowen's reaction series, or this Bowen's reaction series thing that is a little bit simplified. I don't know. Does that resonate? Why should we talk about this, as you said, oversimplified version in intro classes? To me, that's why. Like, it's a good way to introduce some of these key concepts. I don't know. Does that resonate?
Yeah, it does.
Yeah, like, I don't know. I can't remember how this went in class 20 years ago, and you probably do it differently today than you did before then. So what's important to you, and what do you convey to students in this regard?
For sure. I love to know the how behind the why. I always want to know why things are the way they are, and especially geologically. So if you go to a place like Mount St. Helens, okay, and you see a diversity of rocks from the same volcano, I want to know why, right? And Bowen's reaction series helps make sense of that in a way, but it's complicated. How can you get this diversity of rocks from the same magma that's feeding the volcano? And then you start to think about, well, okay, what does it look like as that magma traverses the crust from way deep down, then it traverses the crust to come up and out? What does that journey look like? And Bowen's reaction series kind of helps you walk through that, right? If that magma traverses the crust rather quickly, it doesn't have a lot of time to melt the country rock and to assimilate that composition into it, therefore changing it, then it's going to come out more mafic, and then it'll be runnier and, things like that, right? But if it comes up through the crust, it traverses the crust, and it spends a lot of time in various places, and it has time to assimilate the rocks that it's in contact with, then it's going to melt those lower temperature minerals, as we explained from Bowen's reaction series, that idealized diagram. I don't know, does that make sense? It helps me understand what I'm seeing maybe a little bit better. And I love that. I love the mental gymnastics of working through things like that.
No, that's a great one. And there's a couple sort of really nice examples of sort of natural laboratories for testing this. We should probably touch on a couple of them, or one of them at least, at the end of this as we talk about it. But one thing that comes to mind, Chris, is how is this? Do you cover one or a couple of these types of things in class? Do you subject your students to looking at rocks and saying, "Look at this! This is beautiful. It's Bowen's reaction series at work"?
Oh, absolutely.
Or do you have a lab exercise maybe on this? I don't know. Do you do a lab?
I actually, I guess kind of a lab, quote unquote. It's not really. Are you familiar at all with Palisade sill?
Oh, yeah. Yeah.
Okay. I wrote something up on that. I created a cross-section of it. So what it shows is the composition of this. The Palisade sill is this several 100-meter thick igneous intrusion. Okay. And it's very, very mafic. It was very fluid, very runny, kind of soupy, right? And so I have the cross-section of the rocks above the sill, below the sill, and then the sill itself, this intrusion, right? And all of the minerals that are in it, the compositions that are in it, and the textures that are in it. So I've kind of like overlaid these kind of three things: the cross-section, the chemistry, and the textures that are in the rocks in terms of the grain size, mineral grain size, right? And I have them use the data that's in front of them to explain the cooling history in a very kind of rudimentary way of this sill and the evidence for it. So yeah, kind of.
Yeah, no, that's a good one. I mean, we're sort of here in eastern Pennsylvania, not too far from the Palisades, so it heads north from Manhattan, and it's the western boundary of the Hudson River. There's some really interesting history of the Palisades sill. Actually controlled where the Hudson River flowed, and therefore it controlled where a lot of new development and industrialization took place in the Northeast U.S. So that's a really good one.
One more example of how geology controls everything, Jesse.
It does. It just controls literally everything. But the Palisades is a classic one of this example of Bowen's reaction series at work in a natural setting. There's another really classic example, Chris, an eruption of a lava lake in Kilauea in Hawaii. And this was a really classic example where we actually got to sample this. So there's an eruption, a lava lake formed in a crater, and this lava slowly cooled from the surface downward. And actually, scientists went out and drilled this thing and took samples.
Isn't that amazing?
Yeah.
How cool would that have been? Yeah.
They're really, really valuable samples because they sort of record this perfect crystallization sequence from a natural setting. It applies to Hawaii in this Hawaiian volcanoes. It's not clear how widely this applies, but it's a beautiful set of samples. Actually, we had a paper, I was a co-author on a paper that looked at, and this is just an example that people have used these for, going on 60 years now, these samples, because, they worked out this Bowen's reaction series, this magmatic differentiation. I was on a paper that we analyzed the titanium isotope composition of these rocks and looked at how the titanium isotopes in the rocks change. And that's a sort of a relatively niche measurement, but these are used as a template. It's kind of like the fruit fly in biology. Everybody studies the fruit fly because we know a lot about the fruit fly. It's the same thing here with this lava lake. And it's a beautiful kind of example of this reaction series at work.
And so what they found, correct me if I'm wrong here, Jesse, but I do talk about this in my class too, because I think it's such a cool, just this natural setting that is way bigger than anyone could ever duplicate in a lab kind of setting, right? And I think that's why it's such a cool thing and valuable. I mean, it's more like what you really get. And they found that olivine crystallized early, but then as they let it cool off slowly and they kept drilling down in and taking samples, they weren't finding olivine anymore. And there's a little bit of debate on this, right, Jesse, in terms of, well, did the olivine react with the melt and come back out as pyroxene, the next mineral down in the Y of the discontinuous series? Or did the olivine sink, right? Did it fractionate out? So I imagine you have a thought on this with what happens.
Well, I've not looked in detail at these particular samples, but we think olivine always fractionates out. From any kind of mafic rock, it's pretty rare to find a rock in any volcanic system that is the most primitive melt that we have. The melt formed at depth, many kilometers deep. If it's basaltic melt in the subduction zone, we're talking tens of kilometers deep. And that stuff, it cooled off since it formed, and it probably fractionated. So we can look chemically. We can look at like the magnesium content, the magnesium versus silica, the magnesium aluminum ratio, like all these kind of geochemical indicators that point to, oh wait, this is not a primitive. This isn't the most primitive thing we have. Olivine was probably lost on its way to the surface. And we go from like close to primitive to very far away from primitive. So yes, I think it's a safe bet that olivine fractionated out probably of this at some stage.
The problem is we can't see it. You can't go find it because it's at the bottom of the lava lake, right? But that's exactly what happened in the Palisades sill. The olivine fractionated out. Now there we get to see it. We get to see the whole cross-section of this massive igneous intrusion. It's exactly what happened, is that the olivine formed early and then settled down to the bottom. But I do struggle with this, Jesse, and tell me if I shouldn't, if I got to let this go.
Sure.
Is that, if you take a metal bolt and you put it in a jar full of honey, the bolt is denser than the honey, but the honey might not let the bolt settle to the bottom because the honey's too thick and viscous. And my point is that these olivine crystals that are forming in this soup of magma, they're denser than the magma now, but if you have any kind of convective flow in the thickness of the lava itself, it may keep those things from fractionating out. Right? Or do I just got to let this go?
No, you're absolutely right. That's how we get phenocryst. That's the typical interpretation for olivine phenocryst basalts, which you can see if you ever go hiking in Hawaii, or we did this, Chris, in the Columbia River flood basalts. If you go hiking through any big basalt province, you see different layers. Some of them you'll find little olivine phenocrysts, and that's the classic interpretation, is that those things grew in the magma chamber at depth and then were carried up in the lava, which is kind of the same thing. It's olivine that has not settled out yet. It's kind of the interpretation that people, typically go for. So I guess you should worry about it, but you don't need to worrying about struggling with it. Like, it's fine. That's totally normal, I would say. And the other thing about these lava lakes, and we can see this, you talked about the Palisades Sill. There's a bunch of other places on Earth where we have these kind of frozen magma chambers where we think not much happened to the magma chamber and we're getting a window into that crystallization sequence. And the final melt in these systems becomes really evolved. So we start from some basalt, something like 45 or 50 weight percent silica, modest amount, like a low amount of silica. And then the end stage is driven up in silica because we're crystallizing a lot of low silica minerals. And so we end up with kind of something akin to granite as the last like dregs of the magma chamber there.
All right, Jesse, so what are the shortcomings then? Can we just real quickly talk about that?
Yeah, absolutely. One shortcoming of this Bowen's reaction series sort of model, I think it's useful to think about what Bowen was doing to do this. In the experiments that he was doing, and coming up soon, we're going to have an interview with Mike Ackerson, who is an experimental petrologist who does a lot of stuff similar to Bowen. But what these experiments that he did was he melted rock and then watched it crystallize, right? Like slowly cooled it down, then froze it, flash froze it, and then looked inside. What do you see? Do that a whole bunch of times at different temperatures. He was doing these in furnaces that were at atmospheric pressure. So they were done at the surface pressures. They were not done at high pressures. So that's one shortcoming I think you can kind of envision, is that pressure probably matters when it comes to minerals that are stable, and pressure matters a lot, it turns out. So that's kind of one potential shortcoming. Things like garnet. Garnet is stable at high temperatures and high pressures. So garnet's not in Bowen's reaction series, but it can be a magmatic mineral when the crust is really, really deep, when we're at 30 kilometers depth. Garnet can crystallize out of a magma chamber. Pressure matters here. The other thing is that the recipe matters, like the water content matters. The amount of fluorine matters. These little things you wouldn't think about have a big impact. And I think one way the way I describe this, Chris, and this is kind of where I stop talking about Bowen's reaction series in general, is just in classes, I just say, okay, it's complicated. If you want to learn more, take a more advanced class. Think about the amphibole structure. Like amphibole or hornblende is like this complete mess of a mineral structure, right? Like, I don't know, Chris, do you have hornblende memorized, the crystal structure of hornblende? I just remember this from mineralogy.
Well, I know the crystal structure of it. It's a double chain silicate, but I don't.
The chemistry, I mean, you look at the chemical formula, it's like a complete mess, right?
Yeah, well, so is biotite, Jesse. Oh my
so
gosh.
is biotite. Exactly. So what
so
happens
complicated.
if you change one part of the recipe? It could really change whether amphibole crystallizes or not, or whether biotite crystallizes or not. So, the recipe matters a lot when we're talking about this. So Bowen's is a massive oversimplification in that recipe category.
All right. I have to ask you this then, and we did not talk about this. So you have no idea where I'm coming from, but
Chris, I rarely have an idea where you're coming from, but
I know. Welcome to Jenny's life. Do you
Poor
think
Jenny.
that there could be maybe a revision of Bowen's reaction series that is coming down the pike, maybe that is going to take these other things into account? And I ask this because, I mean, it has its function, right? It has its importance, but we're beginning to just scratch the surface of maybe how important volcanoes are in the formation and concentration of rare earth elements. Things like this.
Oh, it's so okay. Yeah, this is a really good point. So just the history of Bowen's reaction series, right? There's a lot of stuff that worked it out. In Bowen's time, there was a big debate about whether granites were magmas or not, or whether they were like solid state chemical diffusion. And we'll talk about that more with Mike Ackerson, I'm sure. Then in the 70s and 80s, the experimental apparatuses, the apparati that we used, the experimental charges we used got really good. And so there's this explosion of experimental work that could do pressure and temperature and different recipes. So we really worked out a lot of the details in the sort of 80s, early 90s. The experiments got really, it sort of exploded, experimental petrology. But that's like traditional rocks. Like I would say, we started to play with water content. We started to play with pressure. We started to play with aluminum content. A lot of different parts of the recipe were mapped out. But your point, I think, is a really good one. Because yes, I think with regards to like these weird things, the rare earth element deposits or apatite magnetite oxide deposits, those I think we're starting to see sort of a rebirth of igneous petrology to think about these new questions like pegmatites. Where do pegmatites come from? Experimental petrology can be focused on that. Are they magmas? Are they not magmas? Are they magmas or fluids? Short answer is yes. I think absolutely we can. And there's a lot of work to be done on that.
Yeah. So maybe changing the view to more of a building block, right? Like it's a part of a foundation, if that makes sense.
I think that's right. And I think to summarize my opinion on this, Chris, I'd be curious in your knee-jerk reaction to this. I think Bowen's reaction series is an amazing teaching tool. It's not that useful in the real world. I mean, it is in a couple instances. We've talked about the lava lake. We've talked about the Palisades. So those are rare. It's rare that you go and look at Bowen's reaction series as you see it in the textbook and it works, because things like amphibole crystallize a lot differently if there's water in the magma. And you can't get to that point in an intro level class, but it's an amazing teaching tool to get these really fundamental concepts across. So I don't think we need to revise or abandon it in the intro level classes, but maybe point to how it applies in the modern world. It's a tough one to do that because it's not clear that it does a lot. I don't know. What's your reaction to that?
Yeah, I agree with you 100% that it is this amazing teaching tool. I just wonder, though, if for people that use it, that are exposed to it as like an intro level geology class, and then as they progress through and get deeper into the study of geology and maybe igneous petrology, that it causes confusion maybe.
That's a really good point. How do you, because we could apply that same logic to, I think, that same stuff to like a bunch of different stuff, mantle plumes. How do you think about that, or how do you deal with that issue? Like if you're sitting there teaching a textbook, view, it's really useful to get the point across. But then, if the students progress on, they're going to realize, oh wait, my intro level textbook lied to me.
Right. It happens all the time though.
Yeah. And what do you think about that?
I don't know what to think about it, actually. I mean, this is straight up knee jerk. I have not put a lot of thought into this question that you're asking me right now, but you're right. We talked about this with volcanoes a long time ago and trying to fit a volcano in a box. And it's very difficult to do because every volcano is a snowflake. I mean, they're all different. They have
they're all deeply loved by Crystallize.
Oh, they are. Absolutely. All volcanoes are super.
Yeah.
But it's important to point out, though, that, all right, we're going to put volcanoes in a box, but really that's not a good idea, or that just understand that this is an idealized discussion about volcanism. And there are many, many exceptions to the rule. There are going to be many exceptions to what I'm teaching you. So I think it framed that way, then it opens the door for later on for them to be more open to, oh, okay, I just have to add on to or tweak what I was taught before. We can't start off with all of these intricacies with an intro level class. It doesn't work, but it does, I think, have to be framed that, all right, you're going to learn this is not the complete story. If you go through this, right, it gets more complicated.
But that applies to so many things. I mean, I was just talking about streams the other day, and I had to keep it simple because we have like one day to talk about streams, and I have to keep it simple when I want to talk about stream meanders and all the things we've talked about on this podcast, how plants influence meander patterns, and everything is like that. And I don't know how to frame it because like you have to know the basics. You have to know the basics to get into the higher level stuff, but the basics are often wrong when you start looking in detail, right? Those intro level concepts like Bowen's reaction series is kind of, it doesn't work a lot. And it's certainly not the modern way people think about igneous rocks. So it's a good intro to it though, but I don't know. I remember being very frustrated. Well, not frustrated. Maybe it was actually inspiring for me when I sort of started to think, I think it was in graduate school when I was like, oh wait, mantle plumes are different and igneous intrusions. Like there's no such thing as a magma chamber. At least we don't see like this balloon shaped magma chamber in the earth. That was both interesting and scary and like,
yet again, another lie.
Yeah, exactly. Yeah. I don't know. Do you struggle with this and maybe you get the chance to go in the weeds. This is just a great way.
Okay. Here's an example, Jesse. With my freshmen in just an earth science class in an intro to plate tectonics, we talk about subduction zones, oceanic crust, and so on. And we talk about the fact that, that when this plate subducts, it melts. But it doesn't, right? That's a lie. I can't teach them that. But then when I have them again in geology, I am flat out honest with it. I said, well, a few years ago when you had me, I talked about this subduction and what happens here. And that was just really kind of a lie. You weren't, now let's talk about the role of water in this.
JK.
That's right. But, and they're okay with it. They get it. You can't really, I think when you're talking to 14, 15-year-olds who really have not had any chemistry, then you can't talk about partial melting and the role of water. And that's too in the weeds for them at that point. They get the idea, though, that, oh, okay, well, subduction zones involve a lot of pressure and a lot of heat. And okay, well, then that's not too big of a jump to say, well, then you generate magma from that. Oh, okay, it's good enough, right? Isn't it?
For sure. I agree. I think that's good enough. As long as we sort of are honest, as you said before, are sort of honest about that. This actually brings up maybe an interesting point to end on, or one additional valuable thing that Bowen's reaction series does. And this long-winded comment will come with a question at the end of it, Chris. So don't fall asleep on me over there.
I'll try.
One extra thing that I find valuable about it is it does a really nice job of linking igneous rocks and metamorphism, and it kind of shows you how igneous rocks and metamorphic rocks, there's a big like Venn diagram overlap between these. So I kind of I talk about igneous rocks first and then metamorphic rocks and use this as kind of a tie point between them. So I sort of say, okay, let's work down temperature. Now what happens if we go up temperature? How do you structure this in your class?
Not like that. I think that's actually really smart. I love it because what you're really saying is that certain metamorphic minerals, they form in very specific temperatures and pressure conditions, right? And so I see the tie point between that and Bowen's reaction series, where you have these igneous minerals that form at changing temperatures and changing compositions, those two control knobs. So yeah, I think that's actually really smart to do it that way.
But it does get confusing as well. There's another opportunity for mass confusion, and I just experienced this year as well, because I talk about how pressure is important. When you talk about metamorphism, you talk about pressure is important. So then the students who are paying attention they sort of say, wait, Bowen's reaction series, as you talked about, you didn't talk about pressure. And so how does that impact it? Like, this is weird. You didn't talk about garnet, but you have garnet in all these metamorphic rocks. Like, it's not perfect. It doesn't align perfectly. So it adds, again, it's a struggle. It sometimes adds to like a little bit of confusion. I end up getting pulled down random rabbit holes in lecture because of a really good question by a student who's paying attention, previously.
That is a really good question. Yeah, I've actually never had that question in all of my years.
Yeah, so just a really astute one, let's say. But obviously, then you're like, oh, that's such a good question. We got to talk about it. But
well, yeah, we just finished cutting the geology of the Grand Canyon, and we talked a lot about the importance of the garnets and the Vishnu schist down there because that's a huge part of the story. Because they're great index minerals. They tell us the pressures and the temperatures and where these rocks had to have existed to form these minerals. And now here they are 8,000 feet above sea level, exposed at the surface of the earth. So it's a really cool part of the story.
It's a tough one because you could spend an entire class talking about the Vishnu schist and the Zoroaster granite and the relationship between them and the garnets. But that's a little bit niche perhaps.
So what was your question? You said there was going to be a question at the end of this.
That was my question. How do you tie them together? And then also I wanted to come back because you talked about mineral stability on the surface. So back to your 3 intro level points, like about Bowen's, that this is the order that minerals crystallize. This is the order that minerals melt if you're going up temperature. And then it's a window into mineral stability at the surface. How do you thread those together throughout this discussion?
So when you look at the Y, the top of the Y, the fingertips, that's high temperature. And the trunk of the Y is low temperature. And so the minerals down there at the trunk, the quartz, the potassium feldspar, and the muscovites, let's say, those minerals, they form at the lowest temperatures. They are the last to crystallize out of a cooling body of magma, right? They form closest to the conditions that exist at the surface of the earth. 500 degrees or 600 degrees is a lot closer to what we have outside on the surface of the earth than 1800 degrees, where those early formed minerals are. And so minerals are happiest when they exist in the conditions in which they formed in. And so those lower temperature minerals are going to be more stable then. They're going to be happier, if you will.
Yeah, that's a good one. Yeah, I like that. Sort of on average, a quartz is, what do you find in the most mature sediment out there? It's like a quartz sandstone or a quartz sandy beach. That's like a really mature, beautiful, rounded quartz grains. It's because those things survive for a long time. They get carried down all the way down the Mississippi River, and they survive that process. So
only the strong survive.
Only the strong survive. That's exactly right. That was a great episode. That was a really fun one. I reference sand a lot in my class now because of that. So... Oh, Chris, we should probably wrap this up. I mean, we could go for a long time, but let's point to, first of all, our CampGeo chapter on igneous rocks. We have an entire chapter on igneous rocks that kind of touches on these themes. The metamorphic chapter as well touches on these themes. We also have an interview coming up with Dr. Mike Ackerson of the Smithsonian Institute, who's worked a lot on this, and we'll touch on many of these themes as well. So stay tuned,
can't wait.
guess. For more In the Weeds content, stay tuned.
Cheers.
All right, peace.